Hi, in this video we are going to discuss the origin and classification of overvoltages. So just some basics before we go more in depth in the different type of overvoltages. Basically what you have to understand when you simulate a power system, and especially for transient, is that almost everything is an RLC circuit. When you have a line, when we've seen that in the line section, the line is can be modeled as a pi model. In this case, it is an RLC circuit, but it can be modeled also as a distributed parameter lines. And in this case, it's an infinity of pi circuits, or RLC circuits. Capacitor banks are like that. Transformers are also like inductance with like capacitance, straight capacitance. So a network mainly reacts as an association of RLC circuits, which also means a network have natural frequencies like RLC circuit does, and of course the fundamental frequency. So anytime you apply a perturbation to such a circuit, you will have you will see oscillations in voltage and current which correspond to the natural frequency. You may have a DC component, and you will see then the power frequency taking over. Just as a reminder, the natural frequency of our RLC circuit is 1 divided by 2 pi square root of LC, L being the inductance and C the capacitance. Okay, so just a quick demo. If you are not so familiar with the MTP, maybe as a training, you guys could build this little design. It's not very difficult. It's actually part of Get Started training. Here, what's going to happen? So we have two capacitor banks, and in one simulation we energize both of them. The timing don't really matter. We just close the first breaker, then the second one. When we close the first breaker, again we have here our first network. We have another network here, and basically closing the breaker is a perturbation. It's like a perturbation, and we energize a circuit which is this in parallel of this. The newly formed circuit will have several RLC circuits again. What we can see, and here I will switch to the MTP for this demonstration. Okay, this is the same network but with more details for the capacitance. Instead of having just the capacitance, we have also the wires connected to the capacitance, which are modeled. We'll come back after on all the breakers and so on. So let's focus first on this part of the circuit. Here we see we have a very small inductance, which is the wire inductance, and here a bigger one, which is the network short circuit inductance. As we know, for high frequencies, large inductances like this one will be like an open circuit, right? Because the inductance, the impedance of the inductance is GL omega. Omega is the frequency. Then the opposite, for lower frequency, a very small inductance like that will be like a short circuit. So basically here, if we do some sort of a frequency scan, what we can see is that for high frequencies, here this inductance will be open, and so we'll have here this RLC circuit, where we have this capacitance, which is the grid capacitance, in series with this capacitance. Now, when we go to lower frequencies, this becomes a short circuit, and we have those two capacitance connected in parallel, so we can put them in one. And then we have another RLC circuit, which is the two capacitance in parallel with this inductance. Okay, so basically what we can guess here is that when we are going to energize this breaker, we are going to get two natural frequencies. One is this inductance with the two capacitance in parallel. One is this inductance with the two capacitance in series. So we will see that with simulation. Quickly about this equivalent, it's typically for network equivalent, we have an ideal voltage source and a short circuit impedance. Here you see that we also have a small capacitance. This is a way to fit the first natural frequency of a network equivalent. Sometimes we don't have all data required to model the point of connection to a substation because, for example, the TSO will only give you the short circuit impedance, so you cannot model all the lines and everything, but they may give you the first pole, the first natural frequency of the grid. So then you can, using the equation of the RLC circuit for the natural frequencies of RLC circuit, 1 divided by 2 pi square root of LC, you know L, you can determine C in order to have the first natural frequency, and you can add a resistance here to adjust the magnitude of that. And so that's how you can create some sort of a better model, an equivalent model for this, for the equivalent network when you don't have enough data. All right, so now same thing when we energize the second cap bank. What is going to happen is very similar. You will have one circuit which is between those three capacitances, this one being very small, of course, but so it will basically be between those two. So that's the effect of back-to-back switching. We have between the two capacitances, we have only very small inductances compared to, of course, the rest of the grid. And so when we close that, those very small inductances will create very high transients in between. It's almost mathematically, if you take two capacitors and you connect them one to another, you will have, if they don't have the same voltage, you have an infinite current going from one to another to put them in the same voltage instantaneously. In reality, you have the impedance of the cable in between, which is very small. So you will not have an infinite current, but you will have a very high current with a very high frequency content due to the very small inductance. We are going to see that. It's very similar, actually, if you have a fault close to capacitance, that's what we call the outrush. Then you will have same thing, a RLC circuit with the capacitance, the fault to the ground, and a very small inductance. So very high frequencies, even higher than the back-to-back switching, and high current magnitude. Typically, to reduce those frequencies and current, you will add tuning inductances in series of those capacitors. And so basically you increase the inductance of this circuit, and so you will have lower frequency and lower current and voltage, current magnitude mostly. Okay, so let's take a look at that here. So I run the simulation and open scope view. And I'm going to take a look at the voltage here and the current through this breaker. Let's focus only on phase A to make it simple. And the name of the breaker is simply breaker. Let's focus on phase A. All right, so for the first switching, now I zoom here. We see, I don't know if you guys see it, but we can see, especially in the current, the two natural frequencies. We have the first one here. So if I here measure the period of that, the period is 5.2 milli, milli, and if you take the inverse, it means that the frequency about 190. It's not so precise, right? Because I click fairly not so precisely on the peak, but approximately 200 hertz. And what is the second one? Well, it's actually right there. If we zoom a bit more, here we see that we could have used a smaller time step to be more precise, but it's basically this one. And so if we approximately, again, let's check here the magnitude, it's about 30,000. Again, the precision is not good enough, 40,000. We should re-simulate. If we want to see this more precisely, we should simulate the smaller time step, because you see that here, the definition of this transient is not so good. All right, so two natural frequencies, then if I unzoom, you see that we end up going back in the fundamental, then we switch the second time. Then actually we have a third switching here. And with the third switching, what it is, it's we disconnect the cap bank and we re-energize. And so when we disconnect the cap bank, typically you will have a trap charge. Actually, that's a good question that we could ask is what's the trap charge when we disconnect the cap bank? Well, when we disconnect the cap bank, so you open the circuit breaker always, so when you open the circuit breaker, you will have an arc forming. The arc will extinguish at the zero crossing of the current, so always circuit breaker cut current at zero crossing. And for a capacitor bank, the zero crossing of the current is the peak of the voltage, because there is a 90-degree phase between voltage and current for a cap bank. And so anytime you disconnect a cap bank, you will have the peak voltage basically trapped. And so if you, for example, disconnect a cap bank and re-energize it right away, you end up re-energizing a pre-energized cap bank. And you may be unlucky, for example, if you here trap 1 per unit, then the voltage here will keep oscillating at 60 Hertz and goes to minus 1 per unit, and by bad luck you re-energize this time. Now you have a voltage difference of 2 per unit across this breaker. So the overvoltage will be even worse. Why would you do that? Of course, you never do that. Well, you don't re-energize the cap bank before it's discharged, and so you have resistance to discharge. However, sometimes you just cannot. It's just not your decision. For example, the circuit breaker open when the current stops, and the voltage across the circuit breaker will be, like I said, 1 here minus 1 here, so 2 per unit. And that's a moment, if the circuit breaker is not open completely, where there could be a restrike. And if there is a restrike, then basically you will have an even worse case. So you will have an even higher transient. The breaker will end up being completely open, and this higher transient will be interrupted at the next zero crossing. But because the magnitude of this transient is much higher, it's very possible when the current is cut that the voltage trapped is even higher. And so you may have like that an escalation of voltage. So that's what we see here. The voltage is interrupted here. And then, so I don't know if we can see, yeah, let's take a look at the voltage here in cap bank 2. Yeah, okay, perfect. Okay, so we see when we disconnect the cap bank, 1 per unit is stored approximately. And then when we reclose, we have much higher overvoltage than before, much higher current. And so in this case, we don't simulate next week's restrikes, but it's really possible you have more and more restrikes and the voltage escalation. This can be simulated, by the way, if you use the breaker in EMTP and enable the restrike option. You can simulate that and visualize the voltage escalation. All right. Okay, so as reminders again, what we've done here by hand, you can estimate many things and compare with simulation. Okay, you have here all the information you need. When you simulate the closing, we will discuss more in the insulation coordination course, but when you simulate energizing any of these things, like a cap bank, a line, or a transformer, you should take into account the statistical distribution in circuit breaker closing. When you energize the circuit breaker and you don't have any monitoring device that will make sure the breaker close at a certain point on wave on the voltage, it may close at any time. It may be at a max, close to a maximum voltage point, or near zero, or you don't know. And so basically you have to simulate sensitivity, and you have to do a Monte Carlo analysis and switch the breaker at different time on the period, close to the maximum voltage, close to zero, and anywhere else, but also simulate the imprecision in the closing time. Because of the mechanical nature, a circuit breaker may not close always at the same. The three phase of the circuit breaker may not close exactly at the same time. There is a little mismatch of not so much, maybe 1 millisecond, but for transients it's very significant. So all that is being modeled. We'll discuss that in the insulation coordination, in the rest of the insulation coordination course. If we do the analytic method of the circuit we just did, you see here the natural frequencies we find. Remember, when I measured the period, one was about 200 Hertz, the other one was around 40,000, the not so precise one. So here we find exactly the same thing. So here we replace in the C and L by the actual equations. So I let you take a look at that and go back in the video to if you need to really see what those numbers are. Okay, so some basic knowledge you should have for transient simulations. First of all, the time step. Like here, we saw that the time step for the time step wasn't so good to simulate here the first transient. Okay, you see we have a full period here and we have only 1, 2, 3, 4, 5, 6, 7, approximately 7 time steps to simulate this period. It's not enough. A general rule of thumb will be you need at least 10 time steps for the fastest oscillation you want to simulate. 20 is much better. Okay, so often you take the time step as small as possible, so the simulation length is, the problem then is the computational burden if you have too small of a time step. So yeah, if you typically have an idea before you run a simulation what type of event what type of frequency you expect. For lightning, for example, you will use a time step of 1 nanosecond or 5 nanoseconds. For switching, it will be around 1 micro to 10 micro maximum. So by experience, but the general rule is that when you have a transmission line with distributed parameters, the time step must allow to simulate those traveling waves. So it must be smaller than the time it takes for the surge to go from one side to the other, the delay of the line. But again, here it's recommended to use 10 times smaller than that at least, or 20 times to be better. For the simulation length, it's fairly easy. You have to simulate long enough according to what you are looking. If you do a switching study and you're interested in the maximum overvoltage, then you should simulate 1 or 2 cycles after the switching instant, and that's typically where you have the overvoltage within 1 cycle. If you do an energy study for surge arresters, for example TOV or switching study, well, you need to simulate long enough until you reach the plateau for the surge arrestor energy. So it basically depends on what you do. But most of the time, you know a little bit in advance. I would say some studies where you don't really know in advance how long to simulate are machine startup or transformer energization. So often you need to run one simulation. For example, for the transformer energization, you look at the current, how it decays, and if you haven't simulated long enough, then you redo the simulation. Okay, so quickly for the back-to-back switching. When you do a back-to-back switching, so you have again, like in the example, 2 capacitor banks in the same station. You energize the first one, then you energize the second one. When you energize the second one, you have those 2 capacitor banks sitting next to each other, and because you only have the conductors in between and maybe a tuning inductor, you will have very high frequencies and very high current when you energize the second one. In this case, you may not need to do a statistical study because it's fairly easy to find the worst case scenario. You can close basically the cap bank at the 0 crossing of voltage to get the worst case. But I mean, it's always better to do a statistical study and just find the worst case to be sure. So go ahead and do that and find the worst case of inrush current. So you monitor the inrush current, you find the worst case. Then you have to make sure your circuit breaker can handle that. You have 2 limits. You have the peak current and the frequency, and kind of the combination of both. Okay, so you see for different here different breakers, rated continuous current here. You have the voltage there, and you have some peaks. Okay, you have some peaks for inrush current, peak in current and in frequencies. If the current is too high in the simulation or if the frequency is too high, you have to increase the size of the tuning inductance in order to lower the frequency and the peak current. It's as easy as that. For outrush current, it's very similar, but you will place a fault, so typically you will have higher frequency in this case. Okay, so you have those tables for different class of breaker, different voltage level. All that is from standard here, C3706. So I'll let you take a look at those standards. Okay, so I already actually explained this slide. So the mitigation here is the tuning reactor, which is in series with the inductance. You have several things to check out when you design this series reactor. So of course the breaker current and frequency, that's the first thing. When you have high frequencies, it may also go to the control system. So you need to make sure your control system is immune to frequencies, high frequencies. And if so, you may also want to lower the frequency even more. You also have to take a look at if you have measurements. Okay, the cap bank and the breaker may withstand a certain frequency and current, but it has to be the case also for CTs, VTs, which are inactive devices and typically don't really like high frequencies. Also, you have to be careful of harmonic resonance. This is a typical study for capacitor bank. When you have a cap bank, this changes the natural frequency of the circuit and it may create resonance. So I would say most of the time you add a cap bank to a network and size it, you need to do a resonance study. So find the natural frequencies and then make sure the natural frequency of the new cap bank added will not be aligned with the natural frequency of the grid. So that basically runs some simulations with the entire grid. And visualize if you get a resonance or not. Okay, so just to finish on the case of cap bank, now we are there. Several things you have to do, so energization, resonance, voltage amplification. Be careful when you do a switching study for a cap bank. Do not only check the voltage at the point of connection of the cap bank. Check out the voltage at many points in your circuit, in your network, even 20 miles or kilometers away, even more, because the voltage might be amplified throughout the circuit and you may not get the worst overvoltage at the point of connection of the cap bank. Check for restrike. So this is TRV, Transient Recovery Voltage Study, TRV studies. Make sure the breaker is designed properly. If you energize the cap bank with a circuit switcher, which are those long, it's very slow device, be careful of pre-strike, which may create arcing and voltage escalation, like we discussed. It's possible with the MTP to simulate controlled switching, where each pole are closed independently, and the closing time is targeted to minimize the transients. All that can be simulated as well. If you don't know how, feel free to contact us. We don't have a video on that, but we can explain it to you online. The outrush transients I discussed about that. The resonance typically look like that. You have one point each here. When you energize, you have those overvoltages which last for a long time. This will typically damage surge arresters first because though the surge arresters will start conducting during this time, but it may damage other equipment as well because it's a prolonged overvoltage. All right, and now we get to the topic of this video. It was a fairly long introduction, but we discussed also a capacitor bank. So the type of overvoltages. Why is it important to do a classification? Well, it's because most equipment withstand voltage will depend on the type of overvoltage. For example, for a given apparatus, the withstand voltage for lightning will be much higher than the withstand voltage for switching, which will be higher than the withstand voltage for 60 Hertz or low frequency phenomena. And so we need to identify first the shape of the overvoltage in order to compare to the appropriate indicator. For example, if you are doing a lightning study, you will compare the lightning overvoltage with the BIL, the basic impulse level. Sorry. And if you do a switching study, you will compare with the BSL, the basic switching level. So that's why it's important to know to classify the voltage. Also, we'll see that the models will not be the same according to the type of overvoltage. For example, inductive devices like transformers, for very high frequencies, they will be like open circuits. So for lightning, a transformer is mainly, you will mainly not model the inductances. You will focus on the capacitances of the insulators. So you have the windings on top of each other and some insulator in between that create some capacitances. And so you will mainly focus on that for lightning. For switching, you will consider the inductances. Same thing for surge arresters. A surge arrestor will not be modeled the same if you do a TOV study or a switching or lightning study. We did a video on surge arresters. I invite you to take a look at it if it's not done. Okay, so let's quickly go one by one. So the TOV study, we will go back on more detail after, but the TOV study, it's low frequency overvoltages. So typically it can be like a single phase to ground fault where you have a single phase to ground fault, you will have overvoltages on healthy phases. And according to the type of grounding, effectively grounded or not, the overvoltages on the other phases will be none, basically, or up to 1.72 per unit. And so the time for your protection system to clear this fault, some equipment like surge arresters or other may be damaged. For surge arresters, what we look at here is the energy capability, the TOV curve. So you will compare the overvoltage you get for the length you get it before the protection clears, and compare that with the TOV curve of the manufacturer. We have actually an example I will show you where we created a TOV curve device in the circuit, and as soon as you reach this characteristic, it stops the simulation. And so then you know that you reach the limit of that. So that's something important for TOV. In TOV, you also have, for example, load rejection. So, for example, you have a fault on a line, you open the line, and so then you clear the fault, or if you are overloaded, you disconnect the line. On the healthy part of the circuit, you will have a voltage rise because you cut the voltage, the reactive power, you cut the power, the reactive power, you will have voltage rise. Also, when you de-energize a very long line, you may have what's called a Ferranti effect. It's the voltage rising on an unloaded line. And so at the end of the line, you may have overvoltages. So you have a bunch, actually, of TOV. Even for resonance can be a temporary overvoltage. And so for all these, what you mitigate mostly is the surge arrestor energy. So, and basically all equipment TOV curves. But most of the time, the surge arresters end up being the first one to be damaged, but you should monitor all the TOV curves. Then you have the slow front overvoltage. So the slow front overvoltage are switching. They are called slow front in comparison with lightning and other type of overvoltages. The range shape for this surge basically take the voltage, the rising time of the overvoltage between the moment where it's basically normal to the peak or close to the peak is between 20 micro and 5,000 microseconds. And then the duration for the tail when it goes back to almost normal is typically less than a cycle. Okay, so that's the characteristic of a slow front overvoltage. You get those when you do line energization, or even worst case are typically line re-energization following a disconnection because of the trap charge, cap bank switching, fault clearing. Well, there are many. It can be actually lightning as well. When you have a lightning striking far away, the time for the lightning surge to come close to your substation, for example, the shape will change, and it may become basically less steep and become a switching surge. So if that happens, you have to compare this lightning to a slow front, so to the BSL, because the time to peak changed. So here, typically what you do, you will monitor the voltage at many places and compare the overvoltages with the limit of each equipment. You will also monitor the energy through surge arresters, especially for high voltage system or extremely high voltage system. You will monitor the energy through surge arrester. Okay, then we have the fast front overvoltage, which are the lightning overvoltage, so similar characteristics, much faster. Okay, the time to peak is between 0.1 to 20 microseconds, and the tail duration is 300. Here now we are going to compare to the BIL of equipment. And same thing, the surge arresters are what we typically mitigate, but also the energy at the voltage at many places. Now there is another type of even faster transients, which we typically find in GIS, a gas insulated substation. So there are very fast transients. See, the time to peak is lower than 0.1 microsecond. Here it takes specific line models, but I recommend you to use, of course, here the wideband line model, but also use a MOMSO calculator to calculate that for GIS. We won't really discuss GIS in this part of the course, but probably eventually we'll release a video on that. All right, so if we now see the summary of all that inside the table, so you see the shape of the waveform that you get during those overvoltages, and also the characteristic. So you will notice that all the time you have a standardized test. Like if you look at transients, for example, you have the slow front transient. This is what you will get in a grid, and this is what you will use for testing. The goal is what you test has a similar shape as what you have on the field, but it's never completely the case because the tests are standardized, whereas on the field you have different length line and so on. If they are close enough, it's fine. If not, you may have to either use frequency-dependent models, or you will have to use some coefficients to take into account those little errors. So it's we will discuss all that right now. Okay, just a classification here on the chart of all the different type of voltages and the magnitude to expect. Of course, for lightning, we expect very high magnitude, but because it's very fast, equipment may be able to withstand them. Here, this is also a convenient summary of the type of overvoltage you will get for certain events, and so you can know what to do basically. Okay, so we discussed, for example, temporary voltage, we have load rejection, we discussed that, faults, but you have some others like parallel resonance or transformer mitigation. So here you have the list from IEEE standard, so it's very convenient. Okay, so what is it doing the insolation coordination? Here you have the standard definition. The goal of the insolation coordination is eventually to determine the dielectric strengths of your equipment, so the size of the insulator, to determine the BIL and the BSL of equipment, and to determine the rate of failure of equipment. What we are going to see is that from some studies, it's not possible to be sure 100% of the time you will never have a failure. Instead, the outcome of the study will be the mean time between failure, which will be, for example, 50 years or 100 years, which means that you will expect failure statistically every 100 years, and economically it makes sense for you. So sometimes you will have on and off results, it's designed properly or not. Sometimes it will be statistical, and we'll have to take a decision based on equipment cost versus risk of failure. When you do the insolation coordination, you have two types of devices for insulators. You have what is called a self-restoring insulation. So that's, for example, the insulator of a line. And the non-self-restoring insulation, that's, for example, a transformer, the winding of a transformer. The self-restoring, it's the definition is after a disruptive discharge, like a flashover, or it recovers completely and goes back to the original properties, to the original insulating properties after a while. So typically, air is like that. A non-self-restoring insulation does not recover after a disruptive discharge, and you have to change the equipment. So most of the time, equipment will be with equipment with winding and so on will be non-self-restoring, and air-insulated equipment will be. Now the withstand voltage. The withstand voltage is the max voltage an equipment can tolerate. That's here where we have a little difference. For non-self-restoring insulation, this will be a limit. With a limit, which means that if you get an overvoltage below this value, the equipment will not be damaged. If you are above this value, the equipment will be damaged. And so when you do your simulations, of course on field it may not be so clear, but in terms of simulations, that's what it is. In terms of simulation, you get the overvoltage. When you apply all the safety coefficient and so on, it has to be below this threshold. For self-restoring insulation, it's not as easy because it's a probability. And you have, for example, the BSL of an equipment is probability 90% of chance to have a flashover. So that's where this statistical result comes into place. So we'll go back to more details on that, especially after we will see in detail switching lightning and see how to use all these indicators. Maybe one thing just to be clear, so the withstand voltage indicator, they are the BSL and the BIL, the switching limit, the lightning limit. For non-self-restoring insulation, they are thresholds, they are level you shouldn't reach. For self-restoring insulation, they are probabilities. All right, so here this is the theoretical procedure to do an insulation coordination study. Okay, it goes in several steps. Okay, so let's start with the first one. I say theoretical because, as you will see, you often have some shortcuts or a procedure you always do. So when you do an insulation coordination, in the end, you don't always look at that. You follow some other guidelines, but this is good to have that in mind because this is the right thing to do. Okay, so the first thing is the system analysis. So this is where EMTP will come into place. Basically, you will model the system in EMTP with the best of your, as well as possible. And so we will describe how to model for switching in the switching video and how to model for lightning in the lightning video. And you determine what is called representative voltage for TOV, switching, lightning, and so on. What is it? A representative overvoltage. So an overvoltage is assumed to produce the same dielectric effect on the insulation as overvoltages of a given class. So if we now go to a more concrete answer, so this is here the standard answer, but the answer you'll find in the standard. If you talk, for example, about switching, and you do a switching study, like I explained, we will simulate statistical study with a Monte Carlo analysis, and you will find you will have a distribution of overvoltage according to the switching time and maybe other unknown. And statistically, you will be able to find a maximum voltage, the voltage that will be never reached. So that's the assumed maximum voltage. So if you do that, that will be your representative overvoltage. If you use some of the curves used in the standard, in the IEEE IC standard, what you will need is, in this voltage distribution, it will be the 2% chance overvoltage of being exceeded. So when you have all your cases, you will have a voltage where only 2% of your cases were above that. So that's your 2% chance. It's called E2. So that will be your representative overvoltage. It could also be the complete statistical distribution, which means the max, the 2%, and the standard deviation, all the points basically of the could be your representative overvoltage. Why it could be all that? Because it will depend then how you process them. If you for example, use those values, why they could be the representative overvoltage? Because then we have some curves provided by standard in order to give you a method to determine the BSL using those values. So that's why it will depend then what tool you use to determine the BSL. That's how you will determine what is the representative overvoltage. If you use the tool we provide in the MTP, the last option is usually what we use, the complete statistical distribution studies. If you want to do a quick insolation coordination without, a quick one, not with the best precision, you will just take the assumed maximum. Do your simulation in MTP, you find the maximum voltage obtained by simulation, or you estimate it statistically, and you say, okay, that's my max voltage. You take a safety coefficient and you decide your BSL based on that. Okay, if you use the 2%, you will use the curve provided by IEEE and IEEE and find your coefficients based on that, and then determine the BSL. And if you use this complete distribution, you will use the tool we provide in the MTP, and we believe we give the best precision here. So that's the second step now. The second step is the determination of the coordination with stand voltage. It's called the protective margin. Okay, so here according to the type of representative overvoltage you selected, this coefficient may be 1. Okay, so it will basically, this coefficient will depend on the method you used, what representative overvoltage you used. So the goal basically of this coefficient is to consider all the imperfection and the simplification that you could have done during the simulation. Of course, if you keep the full set of overvoltage results, well, there is no simplification really. Whereas if you take only the 2% value, here it's a big simplification. And so this coefficient will take that into account. All that will become more clear when we go really to the process of switching and lightning. So actually we are talking switching lightning. So when do we perform one or the other? Well, typically it depends on the voltage level. If you are below 230 kV, the lightning overvoltage becomes the biggest problem. If you are above 230 kV, it will be the switching overvoltage will be the limited factor. 230 kV or 145 kV, they are often you do both. You do switching and lightning just to be sure. TOV is always a problem, so you should always study TOV. All right, so then you will, so we went to the study analysis. Then we had a coefficient which takes into consideration the representative overvoltage method we selected. Now you have to add coefficient which are based on the environment where your network is. When you do the simulation in the MTP, if your circuit is in a polluted place or in a place which is cleaner, it will not change so much. Same thing if it's in high altitude or not, it will not change so much. It will change a little bit the line modeling, but that's it. And so then the result you get, you have to use coefficients to adapt and take into consideration, well, for example, the atmospheric correction factor, the altitude correction factor, and of course, like for all engineering studies, a safety coefficient, because of all the errors that could be made in parameters identification and so on. Here you have some typical values, but I invite you to take a look at the standards to get more precise values. And the last step, when you are the step above, you have all these coefficients, you will get a value of voltage, max voltage for each equipment. And so then it's basically going through the list of BSL and BIL, according to switching or lightning, and select the equipment you want, basically. So the direct BSL just above what you've selected, the voltage you have. Oops, sorry. Okay, so for most equipment, this list of BSL and BIL will be like tables. For self-restoring insulations, sometimes you may not have those values and you may need to calculate them yourself. So here in this section, we'll explain a little bit how to do that. So for self-restoring insulation, like I explained, there is no set limit where above you have a flashover and below a flashover. Here, it's a probability. So the BSL and the BIL, and BSL is for lighting and switching, and BSL is for switching, it's a 90% probability to have a disruptive discharge. Okay, so it's just a probability. Then you have the critical flashover. The critical flashover is 50% chance to have a flashover. Okay, so the BSL-BIL is 90% and the CFO is 50% for switching codes. Okay, then I mean for for whatever impulse you do. And then you have those equipment, they have a certain properties, and so you have some links between BSL and BIL and the standard deviation of voltage in between. So you have the 90% point, the 50% point, and you have all points in between. So the characteristics you have is like that. So the BSL equals CFO multiplied by 1 minus 128. This is the standard deviation and the CFO again. Okay, and so then when you want to do a study, so you will find, for example, a certain voltage, let's say 3 per unit, and you want to know if I apply this 3 per unit to this insulator, what is my probability of flashover? So you have the equation right there. Okay, so often using this equation, you can determine the standard deviation. You know the CFO, you know the BSL, you can determine the standard deviation, and then you can use this equation here to find the probability. All these are incorporated in the tool that we offer in EMTP. If you don't use EMTP, you can do it manually. It's not so difficult, right? They're just equations. Keep in mind, of course, that you have many self-restoring installations. So you may end up having very large Excel sheets here. Okay, so this will be important at the end to know our probability of flashover. We will have our distribution of overvoltage for switching. So we'll run 200-300 cases of Monte Carlo analysis. We will have the distribution of overvoltages, and we will cross the distribution of overvoltages with this probability. And it will give us the probability of failure, basically. So you have some typical values here of ratio, standard deviation versus CFO according to the type of insulator. For example, if for lightnings and tower, if you consider those insulators, it's 3%. For switching, it's 5%. Inside a station, it will be 6 to 7%. Okay, so okay, maybe one other important coefficient here is this one, the 3% chance of 3% chance the voltage which how do I say that? The overvoltage where the threshold where you have 2% of chance to have a flashover if you're above. So here you have how to calculate it. Okay, it's also a link. Often with IEEE and IC you have different notations. So here we try to write both. But yeah. Keep in mind that those values may change if it's in the politic condition. So here I wrote, I gave you a link for a standard case. Okay, so what we saw so far, it was for one insulator. But on the transmission line, you have hundreds of insulators. And when you have a switching surge, you will have the switching surge traveling through the line. And so all the insulators will see this. And so if you have, let's say, to simplify, 50% chance for the first one to have a flashover, then you have the second one which has 50% chance. When you go through the whole line, you basically combine with this probability. Okay, and so the probability of flashover becomes much higher because you have all of them. And so here we consider that, let's say you have M insulators, so this is how you do to combine those probabilities. Okay, so the first step, you can do some assumptions, of course. For example, when you do a lighting study, you can assume the transmission lines, all insulators will see the same overvoltage, which is a correct assumption, except maybe if you have surge arresters, because often the surge arresters will tend to create a bubble effect where the overvoltage close to the surge arrestor is lower than in the middle. But you can use reasonable assumptions and cut the line in pieces. And so then basically you will calculate like that several characteristics. The characteristics you will need eventually, I can tell you now, are the CFO and the BSL. So you can calculate the CFO, the BSL for several sections of lines, the equipment, and have all those saved somewhere for your analysis. And so if you have an entire line with no surge arresters, that's how you do. And if you have surge arresters, you can just cut the line in smaller sections and assume the voltage will be the same for the section, which is a safe assumption. All right, so now for gaps. So when you have two conductors and a gap in between. Okay, for example, a conductor close to a tower or a conductor going through a tower. How do you determine those characteristics? Well, everything is written there. Okay, so the CFO, which is U50, can be calculated here for the different type of analysis, switching, lightning, or power frequency. Here, Z is the standard deviation. Okay, so we switch a bit notation between IEEE and IEEE. D is the distance between the two conductors. Okay, so you have here the different equations to use. So nothing so difficult here. Well, one thing you will notice is you have this coefficient K. K, it's called the gap factor, and you will see it will depend on the configuration. We'll discuss that on the next slide. So that's the first thing to notice here. Second thing to notice here is like, it seems you have some signs, and it seems you have different withstand voltage if the surge is positive or negative. So that's something also to consider it's something which is true. For lightning, the sign matters. If it's negative or positive or negative, it's not the same. Okay, so keep that in mind and we'll come back to it later. The gap factor, this K factor, okay, you have here a little table that explains you what to select. Okay, so if you have here a transmission line, K, you will take this value. Okay, so you just have basically to have that in mind when you do your study. Here again, we are in the case where you have to calculate yourself the BSL, the CFO. Maybe all these things will already be calculated, and you already have the CFO, the BSL, and in this case, you don't need to do all that. But if you have to calculate them, that's the procedure here. Okay, so far we've discussed mainly, we discussed overvoltage, and it was mostly actually we discussed phase to ground overvoltages. Now, how does it work for phase to phase? Well, for phase to phase, we have to apply a little coefficient. As I just explained, there is a difference when you have a surge which is negative or positive. For phase to ground insulation, we don't really care because the sign it can be plus minus. In terms of simulation, it doesn't change much. So we'll just compare to assume the worst case. Or the worst case, I don't remember if it's positive or negative, but whatever. We'll consider the worst case. But if you consider phase to phase now, it becomes important because the signs matters. Okay, so what we're going to do is when you do your switching, so you run your worst case scenario, then you visualize. Okay, and so you will take here the peak voltage, and where you have those peaks, so you will look at the value on the two conductors, phase A and B, for example. You will take those, you will save those values, U minus and U plus. Okay, so that's how you will calculate this, the coefficient, the coefficient. So maybe U minus will be on phase A, U plus will be on phase B, or maybe it's the opposite. All that again doesn't matter. The important is to find those. Okay, so then you will calculate this alpha based on those. Here it's an explanation I gave before, but maybe more precise. Why it's important? It's because the propagation of streamers and leaders in air gap is different if it's positive or negative. Okay, and so then how we are going to determine this representative overvoltage? We will use this coefficient here. U0, it will be U plus beta U minus. Okay, and so beta will depend on the conductor's position. You have the two conductors in the line, B and C. I focus on BC, but you do that for A and B for all of them. Okay, and according to the distance, you will calculate the B factor. I will show you some equations, but you have also here the reference to calculate them. Okay, so you take the maximum voltage on one phase, the maximum negative, at one point, sorry, you take the plus value on one phase, the minus value on the other phase, and you do this thing. Okay, so now here you can use this, this kind of gives you the value of beta. Okay, what it changes though is that if you have the plus sign, which is much higher than the minus sign, you will just take the U0. So basically beta will be equal to 0. So you will take here U0 equal U plus. If you have this ratio, now U0 equal U minus. Okay, and then in between, that's where beta will have a certain value. You can also look at that with alpha. It may be easier. So if you just take alpha, you will have here this curve to determine what is U0. Okay, so what I just explained here is written in all areas. So you consider U minus 0, UB 0. So that's how you will determine. That's how you determine here the equivalent, the representative voltage, when you will base the analysis on. Then if you're in between, okay, so it will kind of depend here on if it's the conductors are very high or very distant. If they are very high, you will take beta equal 1. If they are very distant, you will take beta equal 0. Okay, so that's, you have to do this little analysis for face-to-face installation. Most of the time, you end up being in a spot where it simplifies by itself, but you know, still you run the worst case, check the different peaks, do some configurations, and make sure to do that right. Basically, to sum up, you have three cases. The case where they are very high, okay, where the height is very much larger than the distance, then beta equal 1. If the height is much smaller than the distance, beta equals 0. In between, if the radius of the electron is large compared to the currents, you take beta equal 1. If you have a short clearance, you take beta equal 1. If you have a long clearance, then you will you go to the next slide here and we'll explain how to calculate beta. Okay. So to calculate, basically you will have here your ratio D versus H, and you will use this curve to find the degree here. And the degree here, okay, will be the tangent. You will find beta because thanks to this degree. It seems a bit, you know, difficult like that, but just follow the procedure, and it's a pretty automatic process at the end of the day. Okay, so for the representative overvoltage, remember you had to assume, and but sometimes you work with percent. Okay, so if you work with the percent, then you also need to do some a little math here to calculate. So the E2 value, which was one of the possible representative overvoltage, you will need to calculate them. So first you calculate the coefficient F and F1 and F2 based on those calculations, and then you will estimate that based here on the what you will use at the end to select your BSL will be based on the analysis was just done on the face-to-face and the analysis done on face-to-ground. Okay, so the value that we just calculated here, okay, and the one if you consider phase to ground, and that will give you the representative overvoltage for the overall study. And similarly, you have here the maximum voltage, what is called the trunk catcher voltage, the maximum assumed voltage, and the standard deviation. They are all calculated like that. All right, here a little, I repeat a little bit. Again, the BIL, the BSL is the we don't have probabilities here, it's 100%. Yeah, one thing on this slide though is for low voltage, sometimes the BSL is not provided, and you only have the BIL. In this case, you have some section in the standard where you can basically, it's over here, you can have a conversion factor, even the BIL, how to calculate the BSL. Okay, here you have the tables provided by standard. Right, so thanks for watching this video. I hope it will help. In the next videos, we are going to work on the switching and lighting independently and apply basically this procedure to switching and lighting. Thanks for watching. Bye.